Welcome to aminacademy.com. In astronomy, let us discuss about electromagnetic spectrum. Objects in the universe send out an enormous range of electromagnetic radiation. Scientists call this range the electromagnetic spectrum, which they have divided into a number of categories. The spectrum is shown in figures. The electromagnetic, that is EM spectrum, is the range of all types of EM radiations. Radiation is energy that travels and spreads out as it goes. The visible light that comes from a lamp in your house and the radio waves that comes from radio station are two types of electromagnetic radiations. This is different kinds of radiation is given. What is electromagnetic spectrum? The electromagnetic EM spectrum is the range of all types of EM radiations. Radiation is energy that travels and spreads out of as it goes. That means wherever it goes, it spreads energy. Yeah, the visible light that comes from a lamp in your house and the radio waves that comes from your radio station are two types of electromagnetic radiation. The other types of EM radiation that makes up the electromagnetic spectrum is microwave, infrared light, ultraviolet light, X-rays and gamma rays. We know that more about the electromagnetic spectrum than you may think. The image below shows where you might encounter each portion of EM spectrum in your day-to-day life. Look at here. This is a long range. Here, look, first it starts with radio waves. AM radio, amateur radio, these are for examples. This aircraft communication. These are radio waves, more wavelength. More wavelength means less energy. Next is microwave. Microwave one example. For this microwave radiation, microwave oven that you are using in a home is microwave. Next, even that infrared radiation. In that, TV remote control, night vision goggles. These are infrared radiations that wavelengths are reducing. Next, visible light. After infrared, that visible light range comes. In this radiation you can see in our naked eye. Ultraviolet. Ultraviolet from the sun, it comes shorter wavelengths with higher energy. Further, wavelengths are shorter and shorter. That X-ray is this range, and gamma rays is further very less wavelengths but more frequencies. The electromagnetic spectrum from lowest energy, longest wavelength at the top, the highest energy, shorter wavelength at the bottom. At the bottom, highest energy, lowest wavelength. Radio. Normally our radio captures radio waves emitted by a radio station. Bring your favorite tunes. Radio wave are also emitted by stars and gases in space. Microwave. Microwave radiation will cook our popcorn and other things in just a few minutes. Just a few minutes it can cook. But is also used by astronomers to learn about the structure of nearby galaxies. Next is infrared. Infrared, that is night vision goggles, pick up the infrared light emitted by our skin and objects with heat. In space, infrared light helps us to map the dust between stars. Next is visible range, visible light. Visible light, our eyes detects visible lights, fireflies, light bulbs and stars all emit visible light. Next is ultraviolet. Ultraviolet radiation is emitted by the sun and or the reason skin turns and burns. Ultraviolet, if directly it fall on your skin, it burns the skin. Burning sensation we are getting. Hot objects in space emit UV radiation as well, ultraviolet radiation. X-ray. A dentist uses X-ray to image your teeth, and airport security uses them to see through your bag. Hot gases in the universe also emit X-rays. Gamma rays. Doctors use gamma rays imaging to see inside your baby. The biggest gamma ray generator of all is the universe. Is a radio wave the same as a gamma ray, or radio waves completely different physical objects than gamma rays? They are produced in different processes and are detected in different ways, but they are not fundamentally different. Radio waves, gamma rays, visible light, and all the other parts of the electromagnetic spectrum are electromagnetic radiations. Electromagnetic radiations can be described in terms of stream of massless particles like photons, each traveling in a wave-like pattern at the speed of light. Each photon contains a certain amount of energy. The different types of radiations are defined by the amount that energy found in the photons. Radio waves have photons with low energies. Microwave photons have a little more energies than radio waves. Infrared photons have still more than visible, then ultraviolet, then X-ray, and the most energetic all are gamma rays. How to measure electromagnetic waves? Electromagnetic radiations can be expressed in terms of energy, wavelength, or frequency. Frequency is measured by in cycles per second or hertz. Wavelength is measured by meters. Energy is measured by electron volts. Each of these three quantities for describing EM radiations are related to each other in a precise mathematical way. But why have three ways of describing things, each with different set of physical units? Here, look at here. This end is gamma rays, this end is radio waves. In between, visible light between these two ranges. Normally, the wavelength is not an Armstrong unit. Armstrong unit is 10 power minus 10 meter. Here, why we put telescope in orbit? Here, we cannot keep telescope near to range of that surrounding Earth because it absorbed. So that the Earth's atmosphere stops most types of electromagnetic radiation from space from reaching Earth's surface. So look at this illustration. This illustration shows how far into the atmosphere different parts of EM spectrum can go before being absorbed. Only portion of radio and visible light reach the surface. Most electromagnetic radiation from space is unable to reach the surface of the Earth because most of them absorb. Radio frequencies, visible light, and some ultraviolet makes it to sea level. Astronomers can observe some infrared wavelengths by putting telescopes on mountain tops. Balloon experiments can reach 35 kilometers above the surface and can operate for months. Rockets flights can take instruments all the way above the Earth's atmosphere, but only for a few minutes before they fall back to Earth. For long-term observations, however, it is best to have your detector on an orbit satellite and get about it all. It works for long years. These are the table for spectrum electromagnetic of radiations with the region, wavelength in Armstrong unit, wavelength in centimeters, frequency and energy. This is from this we can get some ideas about what is their frequency, what is its wavelength and energies. Radiation and temperature. When an object is hot enough, you can see the radiation it emits as a visible light. For example, when your stove top in kitchen burner reaches 1000 Kelvin, that is near to 726 Celsius or 1340 degrees Fahrenheit, it will glow red. All objects actually emits radiation if their temperature is greater than absolute zero. Suppose Only the absolute zero have no hotness. Above absolute zeros, all body have anyhow little hotter than others. If the temperature more and more, it emits more radiation, so it becomes more hotter and hotter. Now let us discuss about radiation laws in short. First, Stefan Boltzmann law. The total radiant energy emitted from a body is proportional to the fourth power of the absolute temperature. Energy Boltzmann energy is equal to sigma T power 4, where sigma is a rational constant. T power fourth power of the temperature. Next, Planck's law. It states that the total electromagnetic radiations emitted by a body is not emitted continuously, but is made up of the discrete units of quanta of energy. This is a Planck's law. That means energy is not continuous. It is continuous, not emitted continuously, but is made up of a discrete units or quanta of energy equal to hv, where h is a Planck's constant, v is frequency of radiation, sometimes written as hf or hv, giving expression equal to hf. Here Planck's constant and Planck's constant in Joule second is given, with electron volts also is given. Wein's displacement law. It explains that fact that objects emit different wavelengths from the spectra at different temperatures. That means if temperatures are changing, its radiation's wavelength also changes. For example, hotter objects emit shorter wavelengths, hence they appear reddish, whereas colder objects emit long wavelengths, hence they appear blue. This is the Wein's law. Lambda max, that is wavelength, maximum wavelength is Wein's constant, that is 0.0029 meter Kelvin divided by the temperature in Kelvin. So this is a lambda max. So far we discussed about what is electromagnetic spectra and their different laws. Then some more explanation about each spectrum, that is gamma rays, X-ray, ultraviolet rays, infrared, like we explained shortly. We have done. Please subscribe our YouTube channel.